We're going to work on a heating curve problem. A heating curve is a graph that depicts how the temperature of a substance changes as heat is added to it at a constant rate. So a heating curve just shows us how temperature and phase changes as energy is added. In this example, we have a heating curve of water, H2O, and the way we want to look at this is if we start here, H2O is a solid, and as we add heat to this, our solid starts to cool or warm up to 0 degrees Celsius. 0 degrees Celsius is where water freezes, and in this area, we have solid getting converted to liquid. So at this constant rate, this plateau, we have two phases here. We have solid and liquid. As we continue to add heat, our liquid starts to warm up, and this region is all liquid. So as we start adding heat, our liquid starts to warm up till it reaches 100 degrees Celsius. At 100 degrees Celsius, that's the boiling temperature of water. So at 100 degrees Celsius, our liquid starts to boil or get converted to gas. So in this region, we have liquid and gas. Now, it's going to keep boiling, or we're going to keep adding energy. It's going to stay constant for a while till all of the liquid gets changed to gas. Then in this region, we have our H2O gas. So typically with these heating curve problems, we usually are asked to solve for the heat for the total change of the substance that we're dealing with. We're going to deal with a few formulas here, and Q equals MC delta T is going to be the formula that we use when no phase change has occurred. So we're either talking about all solids or all liquids or all gases. When we actually change our phases, we're going to have to use a different formula. Q equals M times delta H. M is mass in grams, and that means that delta H is given to us in some unit of energy like joules per grams. If our delta H is in some energy units like joules per moles, then we're going to have to use Q equals N times delta H, N meaning the number of moles. Let's take a look at an example. In this example, we're asked what is the total amount of heat released when 94 grams of water at 80 degrees Celsius cools to form ice at negative 30 degrees Celsius. The first thing I like to do is make sure I collect all my given information and try to understand what parts of the heating curve we're talking about. So we're talking about water that starts off at 80 degrees Celsius. So we're talking about the substance in this region. And it says as it cools to form ice at negative 30 degrees Celsius. So we have liquid water in this region. And we're going to start cooling it down to ice, which is this region. And then we're going to cool it even further till it gets to negative 30 degrees Celsius. So if we kind of extend it, it's this area, and that means we have a solid. So we've got three transitions we're talking about here. So let me start off with my given. I want to understand that we're talking about three transitions. It's asking us to solve for the total amount of heat being released. They start us off with the mass of water. Initial temperature is 80 degrees Celsius. We know that it cools to form ice, so that's going to be my second temperature. Ice gets formed at 0 degrees Celsius, and then that ice cools even further to negative 30 degrees Celsius. I also have some constants that I can grab from the book or from a table. The specific heat of water in the liquid phase is 4.184 joules per grams per Celsius. I also have the specific heat of water in the solid phase as 2.087 joules per grams per Celsius. I also can find on a table the heat of vaporization for water. But I also want to remind myself that vaporization is liquid to gas. I just want to remind myself that. And I also have the heat of fusion as 334 joules per gram. And heat of fusion just means solid to liquid. All right, I've got all my given information. I look at the heating curve. I realize that this requires 3 transitions. Now let's start working out the problem. I'm going to divide my work into these 3 transitions. So in my first transition, I have liquid cooling, meaning there's no phase change. So I can write that down, no phase change. If there's no phase change, then I can go ahead and use the formula that I'm familiar with, Q equals M times C times delta T. We are in the liquid phase, so I'm going to use the specific heat for liquid water. Go ahead and plug in my numbers. Delta T is going to be final minus initial. So Q1 is negative 31,500 joules. For my second transition, I'm talking about freezing, which is liquid to solid. So there's been a phase change. Because there's been a phase change, I'm going to have to use one of the newer formulas, which is Q equals M times delta H. I'm going to go ahead and plug in my numbers. I do have the mass, and I do have the delta H of fusion. Now, fusion is solid to liquid, but I'm going from liquid to solid. So I'm going to try to remember that I need to take the negative of that delta H, because freezing is just the opposite of fusion. So Q2 is equal to negative 31,400 joules. We also have a third transition, and in this third transition, I just have solid cooling. So I really don't have a phase change. I'm just in the solid phase here. If I don't have a phase change, I go back to my old formula, Q equals M times C times delta T, except that my C has to be the specific heat for solid water. Delta T is final temperature minus initial temperature. So Q3 equals negative 5,890 joules. All right, let's not forget that they did ask for the total heat transferred. So that just means I'm going to have to add up Q1 plus Q2 plus Q3. So Q total is negative, oopsie, 68,800 joules. That's our boxed in final answer. Good luck and keep practicing.